Hello everyone. In this video, we are going to discuss a numerical on round-robin CPU scheduling algorithm. So for this particular numerical, you're provided with the burst time of the process and the time quantum for execution. But if along with the burst time and the time quantum, if you are provided with the arrival time also, how to solve such a numerical is what we are going to discuss. Now, first step is calculate the number of time quantum slots the process is going to take. For example, if the time quantum is 2 milliseconds and the process burst time is 11, so it's going to take around 5.5 time quantum slot for execution. P2 for 28 burst time and 2 millisecond of time quantum, it needs 14 time quantum slots. For P3 with a burst time of 2, it just needs 1 time quantum slot for execution. So calculating these slots will help us to verify our Gantt chart that we are going to see in the next slide. So this is the Gantt chart for the given numerical. As you can see, it appears to be a bit more complicated compared to the other scheduling algorithm. You need to be little cautious and vigilant while solving the round robin in order to avoid any mistakes. Okay, so as usual, the first step that you're going to do is to draw an empty Gantt chart and then plot the arrival time of the processes. So P1 is arriving at time 0 and P2 is arriving at time 5, P3 is arriving at time 12, P4 is arriving at time 2 and P5 is arriving at time 9. So plot the arrival time of the process. Before we proceed, you need to understand one more concept here, and that's the concept of a ready queue. So ready queue is basically a first in first out queue. It contains the processes that are ready to be executed on the CPU. In round robin, the process which is at the front of the ready queue is picked up for execution, and the CPU is going to execute that process for a given time quantum. After the time quantum expires, the process is added to the end of the ready queue. And also, any newly arrived process is going to be added to the end of the ready queue. So basically, how round robin works, it picks up the process which is at the front of the ready queue, executes for that given time quantum, and once the time quantum expires, it is process is added to the end of the ready queue, and the next process which is at the front of the ready queue is taken for execution. So with this understanding, let us start. So here you can see this is a sequence of processes that are going to appear on the ready queue for this particular numerical example. For time now you assume that only P1 is there in the ready queue, because at time 0 only process P1 is there in the system. So P1 is given execution on the CPU. Time 2, P2 is entering into the system, so that is added to the ready queue. Now after P1 completes its execution, it is taken off the CPU and added to the end of the ready queue. Right now, as P4 is at the front of the ready queue, it is taken for execution. So P4 is executing. Right now, once P4 has completed its execution, it is added to the end of the ready queue. Right, and then P1 is given the execution of the CPU. So here you can see when P1 is executing at time 5, P2 is entering the system. So P2 is added to the end of the ready queue. So we have process P4 and P2 in the ready queue now, and P1 is executing. So once P1 completes its execution, it is added to the end of the ready queue, right? And then P4 starts executing, right? P4 starts executing. P4 is executing. In the ready queue, we have P2 and P1. Once P4 completes its execution, it is added to the end of the ready queue, and P2 is given the execution. So now as P2 is executing, there is new process P5 entering in the system. So P5 is entering in the system. So we add it at the end of the. So what is the content of your ready queue now? P1, P4 and P5. This is the content of your ready queue. And P2 is executing. Once P2 completes its execution, it is added to the end of the ready queue. It is added to the end of the queue. And then P1 is given the execution. Right, now P1 starts executing. So once P1 completes its so here if you see once P1 completes its execution, when P1 is executing, I'm sorry here, when P1 is executing at time 12, P3 is entering the system, isn't it? So you can see P3 is added to the added to the ready queue. So if you observe here in the ready queue, we have P4, P5, P2 and P3. These four processes are there in the ready queue and P1 is executing. Right? So once P1 completes its execution, it is added to the end of the ready queue. So now P1 is in the ready queue, right? And then P4 is given the execution of the CPU. P4 executes, right? So once P4 completes its execution, now it is added to the end of the ready queue. Right? Now at this point, all the processes have arrived into the system. Hereafter, it's going to be simple. You just follow the ready queue. Okay, so P4 is added to the end of the ready queue, and next process P5 is given the execution. Right? Once P5 completes its execution, it is added to the ready queue, end of the ready queue, and P2 is given the execution. Right? So after P2 completes its execution, it is added to the end of the ready queue. Right? And then P3 is given the execution. So here P3, it has got just one time slot, right? It has got a burst time of 2 milliseconds, one time slot. So you can see P3 has completed the execution. P3 will complete its execution. So you can see I have shaded here. This indicates that particular process completes the execution here. So now it is not added to the end of the ready queue because it has finished its execution. Right? So after P3 leaves the CPU, we are going to see the ready queue and P1 is at the front of the ready queue. So P1 will execute now, right? Once P1 completes its execution, it is added to the end of the ready queue, right? And then next P4 will execute. After P4 executes, yeah. After P4 executes, P4 should be added to the end of the ready queue. So here P4 should be there. Here P4 should be there. Okay. Here P4 is missing. P4 should be there. P4 should be there. Okay. So P4 is executed, and after P4 is added to the end of the ready queue, P5 is executed, is given the CPU. Right? After P5 completes its execution, it is added to the end of the ready queue, and P2 is given the CPU. After P2 completes execution, it is added to the end of the ready queue, and then P1 is given the execution. P1 is completed execution, it is added to the end of the ready queue, and then P4 is given. So now like this you're going to continue this execution. You need to see how much time, how much slots each process has executed. For example, here P1, it needs 5.5 slots. So let us count here. P1 1. So let us count the time slots for P1. So 1 2 sorry 1 2 3 4 5 and 5.5. So here you need to understand that you have to complete the process execution of P1. Similarly P2, 14 time slots, 1 and then 2 and then 3 4 5 6 7 8 9 10 11 12 13, probably here one more is there, 14. So like this, you can count the number of time slot that the process has taken for execution, and you can verify whether that particular thing is correct or not. So like this, you need to carefully draw the Gantt chart for round robin. It is actually simple. If you solve one or two simple problems first, and then take a complicated example, it will be very clear. You just need to keep track of the ready queue. You can perform this computation on a rough page and get it done. So once this Gantt chart is ready, you need to next calculate the wait time and turnaround time. So if the Gantt chart is perfect, you're not going to make mistake in the waiting time and turnaround time. So here I'm just going to take a little different approach to calculate the waiting time and turnaround time. So first thing is, turnaround time is the time when the process completes its execution, the time taken by this process in the system to complete its execution. So here for process P1, if you see P1, it has arrived at time 0. It completes its execution at time 37, right? So 37 minus 0 is the turnaround time for P1. So turnaround time for P1 is 37. Now I'll take a reverse approach. To calculate the wait time of the process, I'll subtract the burst time from the turnaround time. So what I've done here, from this Gantt chart, I got to know the turnaround time. From this turnaround time, I'm subtracting the burst time. So 37 minus 11 will give me the waiting time for P1. Similarly for P2, if you see, P2 has arrived into the system at time 9. When did it complete? At time 67. So 67 minus 5, 62 is the turnaround time for P2. Right? Then what will be the waiting time? 62 minus 28. Turnaround time minus burst time will give you the wait time, 34. Similarly for P3, you can see, where did P3 end here? P3 is ending at 20. When did it come into the system? At time 12, right? So 20 minus 12, 8, right? Then what is the waiting time? 8 minus the burst time of P3 to 6. So like this, you can calculate the turnaround time first from the Gantt chart. Basically, when the process completed its execution minus when the process arrived into the system. For example, P4, it has completed its execution at time 32. When did it arrive? At time 2. So 32 minus 2, 30. Right? So that is the turnaround time for P4. So what is the wait time? This turnaround time minus the burst time 10 is the wait time for P4. Similarly, let's see for P5. P5 is ending here at 55. Right? When did it come into the system P5? At time 9. So 55 minus 9, 46 is the turnaround time. And then what is the wait time? 46 minus 16 is the wait time. So once you calculate the wait time and turnaround time, just take the average of this. That will give you the average wait time and turnaround time. I hope you understood this problem. Solve simple problems first and get your concepts cleared, and then you can attempt to solve a little complicated problem. Thank you.